It's the parallel plate capacitor, simple form. So in essence, what we're going to do is just measure the capacitance between these two plates. To do this, we have a meter right here which measures capacitance. So you put that on the capacitance symbol, and it's right now registering a very small amount. Now we don't need to use the probes specifically. We can use these banana plugs. This is a standard, and they fit right in there. And I can do one on the other side also. This is not polarized, and so it doesn't really matter if I have the black in this side or the black in that side, but I'm just doing it for why not. Notice that there is sort of a default amount of capacitance right there. Let's let it sort of settle down. So that is a default when nothing is in between. I can move this a little bit farther out. It doesn't really seem to change it a whole lot. Notice what happens is if I touch them together and we wait long enough, because right now what the multimeter was doing is it puts charge on it, and basically it's looking at how much charge it can put onto the plate, or how much effort does it take to put charge onto the plate. And so when they're touching, we get the OL, or overload. In other words, it is a huge amount of capacitance just because it's able to, from the machine's point of view, it's able to put more and more charge onto the plate. So either I've got more than whatever the maximum number of microfarads is that I can put on this plate, or I have plates touching them, and so it can put an infinite amount of charge on the plates because the charge is just running right through it. You know, the machine does not tell the difference between really huge plates and plates that are just touching each other. So there's a certain amount of common sense. We know that these plates are not going to get so big. Normally it's in the nanofarad range. But we do want to get the plates as close to each other as possible without touching. And so this brings in the dielectrics. So dielectrics, we have a couple different kinds, but paper is a common kind of dielectric that we can use here. And I can put the dielectric in between, and this allows two things. One, dielectric will boost the monocapacitance just because it produces that counter electric field, which allows more charge to be put onto the plates because there's less pushing against it. And also it allows the plate to get closer to each other without actually touching. So if I have the two plates like this, all right, so we have a capacitance of, looks like about 0.202 nanofarads. And now I've suddenly increased the capacitance. And now I don't want to touch it in case I've got enough oils in my hand to allow conducting. But now I can press them closer together and I get an even bigger one. One of the tricks of this lab is to keep these consistently pressed the same amount against each other as we go, because obviously that can affect it. Now there was one particular semester when people were using textbooks to press them together. They put this down flat on the table like that. They put books on top of it. And some people were getting just bizarre results. And eventually figured out that two of the groups were getting results I would expect, two of the groups were getting bizarre results. That the book that they were using to press down on it had foil inside. And because it had foil inside, it polarized and affected the amount of charge being put on the plates. And so all they had to do was put book without foil in the cover and use that, and they started getting normal results. That was one that I'm glad I figured out that day as opposed to when I was grading them. And so now we actually have to figure out how we're going to do this. And I think I'm going to use the book stacking technique here. And I got plenty of books here. Just need to make sure not one with foil. I did switch out a wire here because I wanted a longer one. And so I'm going to go for the baseline charge again a little bit differently. So I'm going to move the two plates farther apart. And just not sure if the wire makes a difference or not, but move them apart. And this baseline here is the value that we need to subtract from all the later values. So in the lab, there's a reference to measured capacitance and then the capacitance. So the measured capacitance is what shows up here, and then the actual capacitance will be whatever shows up here minus this base value, which I guess is 0.104 nanofarads. Ooh, it's flipping back and forth. On which value does it hang out? more. Well, I'll actually let you be the judge. It's been showing long enough. It's either 0.103 or 0.104. And based upon how much it's on one or the other, you could actually estimate another digit in there if you wanted. So it's somewhere in between there. Hopefully that's enough time for you to draw a conclusion. We now need to measure the dimensions here. We will assume that the dimensions of the plates are the same. It might be a false assumption, but we're still making that assumption anyway. We just need to measure the size of them. I need to get the vernier caliper. So I need to measure the length and width of this. It's going to be standing like this. So from your point of view, like that. This is what I'm defining as the width as horizontal, and that is the length. So the width, and it is close to 10 centimeters, but it's not quite. It's a little bit shy of that. So I'm going to stop this and take a picture. Because of parallax, I'm just going to try to slowly scan here. Let you sort of figure out how that lines up the best. This is for the width of the parallel plate. Now measuring the length or vertical distance of the plate. And it should be roughly the same, but again, doesn't mean that it actually is. And so we can see that it is slightly different than the other one. So you see where the 0 lines up just a little bit past the 99, and then we got the video there. So let's sort of zoom in on some of this. All right, so you can see where the 0 is, a little bit past 99, and so let's see if we can try to eliminate some parallax here. And it's got to be somewhere around here, one of these. And now let's do a photo. We now need to measure the thickness of 10 sheets of whatever we happen to be using here. And so this is where the two labs differ, at least usually in terms of what is done in class. I can actually expand that now, considering you have the same amount of time to do the labs. So let's take out 10 sheets of copy paper. There's nothing on the sheets. That was something that I did run into early on, where I had sheets with writing on them and sheets without writing on them, and I got different values for the capacitance because of the amount of writing on it. So this is 10 sheets of copy paper right here. So we're going to measure the thickness of 10 of them so we can figure out what the thickness of one of them is. This spreads the error out over that. I'm going to use the vernier caliper since that's what I have right here. I could have also used a micrometer. And I'm holding it tight since we are dealing with such small numbers there. And from that, you should be able to get a reading. So you should be able to get a reading for what the thickness of 10 sheets of this paper is, out to the nearest 0.05 millimeters. I have 10 sheets of tissue paper. I think this is toilet paper, but it's 10 sheets of what I believe to be single ply, but as long as it's the same material, it doesn't really matter. So holding that tight, should be able to get an idea of how thick that is. Obviously not as thick as the copy paper. So you see where that's lined up, and then you're looking to see which of the other ones is lined up. So I now have plastic coming from a plastic grocery bag. So we need to figure out what is the thickness of 10 sheets. This is 10 sheets. I already counted that out. That gives you an idea of where it lines up. So it's between 0 and 1 millimeter. And then you can see which one lines up the best. And then lastly, I have 10 pieces of this, and we can find the thickness. And it looks like it's somewhat near that of the copy paper. And we can get a more precise measurement there. I have 10 pieces of paper here, which I'm going to line up. I need to make sure that the top plate lines up as well. And so I'm doing this by looking at the feet. Is it possible that we can blame any inconsistencies on the dog hair? So line that up there. I'm lining up, basically I'm looking at the feet to make sure that it lines up like this and lines up that way. I had gone through this before, and so there's probably some absolutely brilliant commentary that you'll never actually hear. And the issue was, when I found the distance between the plates, when I measured the thickness of the paper, of the 10 pieces of paper, it was because when I was pressing them really tightly together, but here, are they being pressed as tightly together as I would like? And so what I'm going to do is try to get them pressed together as much as possible. So I'm going to put a book there so I'm not actually touching the plates when I press. And actually, let me do it this way so I don't have the curved part up against them. Make sure that that is lined up there. And then let me just sort of press right there. And so that is for 10 pieces of paper. Now let's take a piece off. Make sure it's lined up. 9 pieces of paper. This will be for 8 pieces of paper. This is 7 pieces of paper. Six pieces of paper. Five pieces of paper. Four pieces of paper. Three pieces of paper. That's it for the copy paper. Now for the tissue paper. So it's 10 pieces of tissue paper. Nine. Eight. 7. So 6. So 5. Four. Three. We're about to go through the parallel plate capacitor, except this time using these thick sheets. Now, the difficulty with using plastic is that they do hold charge quite well, and so we need to discharge them as best as we can, and so that's why I'm sort of rubbing the pieces against the metal. The grocery bag is especially bad. Get some really strange results with this sometimes, and it's possible this just won't make it into the final lab version. All right, so cover up the plates, line them up as best I can. All right, so 10 sheets of the thick plastic. Nine sheets of the thick plastic. Eight sheets of the thick plastic. Seven sheets of the thick plastic. Six sheets of the thick plastic. Five sheets of the thick plastic. Four sheets of the thick plastic. Three sheets of the thick plastic. Ten. All right, so this is the plastic coming from the grocery bag. So this is 10 sheets. Nine sheets. This will be for 8 sheets. Seven sheets. 6 sheets. Five sheets. 4 sheets. This is 3 sheets. For this last part, procedure B, capacitance versus plate area. Pick one of the previous dielectrics. So I'm going to choose paper since that's actually the easiest with which to work. And I take the 2 plates and 4 sheets. So I got 1, 2, 3, and 4. If everything's gone right, I should get a value very close to what I got before. Now, what we're going to be doing is, with the dielectric there, we're basically going to be shifting this over 2 centimeters every single time. And so the overlapping area is going to change. And so I'm going to actually start with the paper, that side even with themselves, and then even with this. And that way it's going to be a lot easier to actually measure these distances here. I will also need a way of measuring, and I have a meter stick. Seems like an overkill, but meter stick it is. All right, so I don't need it quite yet. So I'm going to pull it out of the way. I will bring it in when I need it. So let's make sure that all the left sides are lined up. So that should be lined up. I try not to have any paper out this way, just so that I can measure more easily for the next parts. So that's 4 pieces of paper with 100% overlap. Now we bring out the meter stick. I'm going to keep the paper where it is, in theory. And I'm shifting this plate over 2 centimeters. And it usually requires a little bit more coordination than I typically have, but hopefully we get close enough. I want to keep the paper where it is and put this that's 2 centimeters over. Hopefully keep that in place. And the capacitance should drop because I have less overlap. This still, take it over another 2 centimeters. So let's see if I have the 6 there. That's 2. There we go. So recognize that the overlapping area is, so we still have the length going this way, but the width is now smaller by 4 centimeters. Good enough. And again, capacitance is dropping as expected. Okay, that's still lined up there. So another 2 centimeters. So considering the level of precision we had for measuring length and width, and now I'm just sort of eyeballing 2 centimeters, well, that's just the nature of the beast here. So this is 6 centimeters slid. And then we need to go another 2 centimeters. So let's get that lined up there with that edge. And go over another 2 centimeters.
I assume it's all being done perfectly, and anything that appears to be a little bit off is parallax. Of course, yeah, it's physics. Come on. This is having it shifted 8 centimeters, so we have a very small area there. So the way you would calculate the area for, let's just take that as an example, you take the width of the plate minus 8 centimeters, and then it's just going to be that, so that tiny, minus those 8 centimeters, and it's going to be that little tiny bit times the length going in this direction. And so now we go another 2 centimeters. And some will, since the width was less than 10 centimeters, some will put down 0 as the overlapping area, and some will put down a negative area as overlapping. In terms of your data, it doesn't make that big of a difference. I accept either one. And it's not quite at the baseline value, but it is incredibly small because the baseline I think was 0.103 or 0.104 nanofarads. So it's not a lot of capacitance. There are emitter plates near each other. They're just not overlapping at all. And one final comment on there's that part for the 252 lab. There's this part C, you make your own capacitor. That's just going to get dropped for the home edition, unless all of you have a meter that measures capacitance. It'd be very difficult to do. But the essence is, given a sheet of aluminum foil and everyone gets the same starting sheet, I think 1 meter by whatever the width of it is, build the largest capacitor you can. There's a basic technique that most people use that is not optimum, but I can share some of that data at some point if you would like about what people have done and what they could have done.